down to
advanced plan. But it's broken. Not sure you can fix it and then
how we plan on detecting gravitational waves of dark matter with this 100-meter interferometer with the currently So we'll start with some scientific motivation. Violent cosmic events like binary black hole mergers produce ripples across space that effectively result in the 2 points between the distance between 2 points on, say, Earth, oscillating with a fractional amplitude of almost 10 to the minus 21. Now, in 2015, LIGO observed such a strength in space-time. Here's what the signal looked like in the time domain. And for detectors of this kind, it's often convenient to look at the frequency domain. So here's a plot that shows the sensitivity of LIGO. It can typically be interpreted as you can detect an gravitational wave with an amplitude larger than this point. And also notice, one thing worth noticing here is that at lower frequencies, the sensitivity dropped by almost 10 orders of magnitude. And that's primarily due to seismic noise. What do we do? We'll put it in space, of course. Because and there does seem to be a proposal of doing LIGO in space called LISA. Here's an artist's rendition. And here's the sensitivity curve for LISA. Now you might wonder, like, what about here in the middle? Well, it turns out there is an alternate detection scheme, which I'll be talking about, involving atoms and free fall. So here's the scheme where if you have 2 clouds of atoms separated by a distance L, and in this talk, L will equal 100 meters. Then, if you think of these as clocks, I mean, you already guessed the answer, they're optical atomic clocks. So if you have a precise enough clock, you can sacrifice one spatial degree of freedom, like the 2 arms of LIGO, and instead use a temporal one, where you basically time the amount of time the light takes to go from point A to point B. And changes in that will correspond to a strain in space-time. Now, here's a curve which shows the initial sensitivity of MAGIS-100. And this is a dashed line that shows the sensitivity once all the parameters have been optimized. Now, look at we're effectively simulating wavelengths, right? So we should have it should be identical to LISA or anything in space. Well, unfortunately, that's not really true because there's this so-called gravitational gradient noise, which comes from seismic wave-induced density fluctuations in the ground near our detector. So I'll talk about how we plan on mitigating this gravity gradient noise. Right. So the next step would be to once we demonstrate this technology, the next step would be to go to MAGIS-1 kilometer. And to prepare comparison, I'm showing MAGIS-1 kilometer with LISA and LIGO. Now let's look at some actual sources of gravitational waves. Now this line shows the famous one that was discovered in 2015. So you can see that even within a narrow frequency band, you can still detect that one with MAGIS kilometer. Now, one step further, if you do a MAGIS space, then you get rid of gravity gradient noise, and then one thing you can do is also, but this isn't the broadband one. One thing you can do is if you sacrifice bandwidth a little bit, if you measure this resonantly, you can increase your sensitivity. And now the smart thing to do would be to scan across the frequency band, and that's what the round curve represents for here. Now you can see these other sources, neutron star and white dwarf mergers, that can be easily detected by MAGIS space and not the other ones. All right, so switching gears to another field we plan on detecting is dark matter. Well, as the name suggests, dark matter is something that does not interact with light. And it composes almost 5 times that of ordinary matter, so we want to see what that is. Now, because we don't know much about it, the possible spectrum of mass is very broad. So, but very recently, people have gotten interested in the ultralight ones. So, you can think of this as a classical field oscillating with a frequency equal to the constant frequency of the dark matter. And this is the mass range we're talking. And the way we see it is coupling to normal matter through these coupling constants, E, M, E, and E, and that shows up as a oscillation of fundamental constants like the mass of the electron and the quantum constant. Well, here's some curves showing what our sensitivity would be with MAGIS-100 at 1K. And terms of we expect from MAGIS-100. We expect the sensitivity of the noise. So now, as I hinted earlier, we're using strontium, which is known as one of the best atoms to use in optical atomic clocks. So here's the electronic structure. First, we cool down the atoms with the 461 nanometer transition at 1 millikelvin, with some help from these repulse wavelengths. And then we have the much narrower line width transition that brings us to 1 microkelvin. And finally, we go down to nanokelvin temperatures by using a far off resonant dipole trap. Now there's the interferometry lasers. So one is the very attractive 698 clock transition, which we can use to detect gravitational waves and dark matter. And what makes it special is that the lifetime is in the excess of 100 seconds. And for dark matter, we use this 679 in the Bragg mode, which I'll describe later. And assuming we have prepared the atoms in this metastable state. So here's how the radiometer mode works, where you have a cloud of atoms where these two interferometers are separated by a baseline L. And these are the two electronic energy levels. The blue is the ground state, and the red is the excited state. And then the phase that we measure is proportional to omega A L over C. So one thing is pretty obvious that because we're sensitive to the length, we should be able to see a gravitational wave-induced strength. And another thing, a subtle thing to note is that it also depends on omega A, and it's predicted that some dark matter candidates would cause an oscillation in these energy levels, which could also be detected using this technique. All right, so now I'm going to switch to another technique of measuring dark matter. Another way dark matter can be seen is if you take two isotopes of strontium and then launch them up together. Dark matter will make them, couple of them differently, and make their accelerations and affect their acceleration differently. So, as I said before, we use the 679 nanometer 2-photon Bragg transition for this. And the reason we don't use the very nice clock transition is because, unfortunately, the 698 does not easily couple to the bosonic strontium 88 because we can't practically apply a large field in such a configuration. Right, so another thing that makes Bragg transition very attractive is that the nice story is that the atoms are not always co-located. There's always some sort of a kinematic jitter. Like, for example, if there's an offset, then that could cause problems. But unfortunately, so that if the offset, if it couples to the gravity gradient, then it can lead to a differential acceleration that contaminates our dark matter signal. So, but fortunately, there's a trick. If we only shift the mirror pulse by delta k, then we get the expression for the phase shift as given by this. Now, if we set delta k equal to this term completely vanishes, and we're able to measure dark matter without problems. All right, so the Bragg transition does come with some come out of place. You need more power. And the reason is because Bragg transitions are more susceptible to AC star shifts. And that is, if there's a ripple in the wavefront, then as a beam propagates, the ripple will change, causing a change in the energy landscape across the baseline, which is extremely undesirable. So what we do is, if the Bragg beam is detuned here, we use a spectator beam with the opposite detuning and same power to cancel out the star shift. All right, so here's a bird's eye view of the MAGIS detector. Here's the 100-meter tower. The interferometer is going to be located on the wall. So here's a CAD rendering of a section of that same interferometer. On the ground level, we have the laser lab. Then we have the top atom source. 50 meters below, we have the middle atom source. And 50 meters below that, we have the bottom atom source. And here's a zoom in showing the atom source where atoms are prepared here to shuttle into this vertical tube and launch. Now, the reason we have 3 of them is so that it gives us flexibility to measure in different modes. I'll give you a couple of examples. So in this one, if we drop atoms from the top and the middle atom source, this allows us to maximize the drop time. So the amount of time we're interrogating the atoms. And in this configuration, if we launch the atoms from the top of the bottom source, then we get the maximum baseline. So that these two modes are used for gravitational wave and dark matter detection. And the third one, as I said, already said, is for dark matter only, where we launch two co-located isotopes. All right, so here's a picture of the laser system. Here's how it works. We have two titanium sapphire lasers, and in the single photon clock transition, we coherently combine them on a 50-50 beam splitter to increase the power and hence increase our Raman frequency. And when we operated the Bragg mode, we tune one of them red and one of them blue up to 679 nanometer transition. And in both modes, these two lasers are stabilized at an optical frequency home. And if you want to see more details, please see this poster here. Here's a photo of our frequency cone, which is in turn stabilized to this ultra stable cavity. This shows a beat note. This beat note shows the alignment of the order of hertz. All right, so it turns out that our laser system is actually located pretty far from the interferometer, so we have to play a few tricks to deliver the beam without any errors. So here's something we worked on very hard for the past year, where we transport the beam from the laser lab to the interferometer using this 4F method to avoid plane dip, which could lead to doctorships and other problems. Now, so the idea here is map point A to point B. And if we place a relay lenses over here and over here, then we can successfully do that mapping. And then after the beam is delivered there, a little bit of cleanup occurs at the breadboard over here, where the beam is launched into ultra-high vacuum for a beam cleanup. And for more details about this system, please see this poster. All right, so why do we need a beam cleanup? Well, it's because actually I forgot to mention that one of the key features here in the single photon mode and the gravitational wave detection is that any laser noise imprinted on the top is also imprinted on the bottom interferometer, so it's common and then it cancels out. But the only thing that can jeopardize that is if the beam somehow changes, which it won't normally. But it turns out that any optic or any vacuum window has some roughness to it that introduces wavefront perturbations. And here's a simulation showing how those wavefront perturbations evolve. And we can't have that happen between these two. So the idea is let the beam just propagate freely for a while and let these diffract out. And then we can shoot the beam down. And after the cleanup, we only use a very, very high quality optics in vacuum. All right, and for details of numerical simulations, see this poster. All right, so the last thing is we have a tip tilt mirror to change the plane of the beam between pulses. And the reason we need to do that is because the lab is rotating and the atoms are not. And so we have to make the laser beams follow the atoms. All right, and then details of this system can be seen on this poster. All right, so as you see, we were launching these atoms at a slight angle. And how do we do it? Well, here's a neat little trick to launch them, where you have two cross beams forming a standing wave. When the atoms from this atom source are loaded into the standing wave, then depending on some motors over here, the plane of the beam can be changed, and we can launch it however we want. All right, so there's a lot of details in this, obviously, but we don't have time to go over all of them. So I'll just conclude this talk with some future outlook of what MAGIS-100 would want to do. So we call this sensitivity curve. Now, as I foreshadowed earlier, that this gravity gradient noise, GGN, is a bit of a problem. Now, also recall that we have 3 atom sources. Now, if we make it separated by 50 meters, now if we make a 1 kilometer interferometer and then we put 21 of them, then what we can essentially do is we can think of them as mini interferometers stacked on top of each other, and then we can subtract out the gravity gradient noise from our measurement. Now, so as you can see, because the MAGIS-100 is at lower frequencies, we can freeze the events register are expected to register on this months in advance.
So one thing we can do is that once we see some binary radical merger or white dwarf merger, we can send the message to LIGO and other instruments so that they can point their instruments and look for that event in the higher frequency. So this opens up the very exciting possibility of multi-messenger astronomy. So I think I'd like to conclude my talk with that. And I'd like to thank our collaborators. Well, it's not as big as MAGIS, but it's still a team effort nonetheless. Thank you. We haven't actually, not at the point where we are actually going to the 698 yet. So we'll figure out after the installation. Cooling techniques during the time flow? No, we don't. We just rely on, hopefully, the atoms are just really going to expand. So if we go to longer baselines, I can see how the cloud heating up will become a problem, but we'll probably deal with it when we get to it. Yeah.
Can you elaborate on how you observed for dark matter with different isotopes? Will this just be similar to like an equivalent?
Exactly, yeah, that's right. So we basically measure differential acceleration between the two species. Yeah.
And how would this compete with, I guess, the state-of-the-art
So with rubidium, there is a 10-meter fountain at Stanford that does this, which I showed you earlier. That one, as you can imagine, has only a limited amount, a few seconds of drop time. So if you interrogate over, let's say, the 100-meter fountain can give you 9 seconds of drop time. So if you interrogate it over a long period of time, that it obviously boosts your signal. The other thing that's nice about strontium is that you remember the clock transition where we can also detect a change in the frequency. So that's another unique feature which rubidium doesn't have. Rubidium doesn't have that nice little clock transition.
We have one last